do you need to have a certain level of expertise already to be on Kaggler, or is it just like you can start as a novice and go from there?
I think some basic understanding is required. However, that threshold is not too high. Once you understand the basics of machine learning, you can almost jump onto the platform, and they have several practice problems, which have been attempted by some of the best data scientists in the world, pretty much. And you can see the solutions. You have something similar to Python notebooks, I would say, that you can actually that you can have a walkthrough, and most people are really generous in sharing out their ideas, describing what was going on in their mind when they came up with an idea for, let's say, a feature, or why did they choose a model that they actually chose. So early on, I did found it really useful to start with the practice problems and walking through some of the top solutions. So fundamentally, it's like there are several steps, right? You need to start with data cleaning and the missing value imputation, and then comes modeling, and then some kind of post-processing, and probably like another step might be feature engineering right before modeling. So you get a sense of all the possible techniques that you can use in all of these modules by going through tens and hundreds of these notebooks online. So I would say the threshold is not that high, and it is indeed useful to get engaged on a website like Kaggle early on, so that you can have some sense of applied knowledge, except the theoretical one that you're gaining from some other source.
Interesting. Thank you for sharing that. So our poll has been completed. Looking at the profession, most of people are engineers by profession, data scientists, 27%, 40% engineers. We have quite a mix of also business consultants in the project manager, product managers, and not forget the 21% other people. Now it would be, if you want to chime in what you are doing on your professional base, just you can use the chat here, please. It would be interesting for us also to focus the content a little bit better and to make it a good experience for all of you guys. What is your level of experience with today's subject? We have a lot of really beginners, so people who are obviously interested to get a kickstart from here. Practitioners, 38%, and we have some experts as well, which is cool. So the experts, just to call in around here. If you feel free to add your experience as well at any time, it makes sense. So cool, that's awesome. So going back to closing the poll again. Just how we're going to use the system, please. The chat for quick information to the round, but we have also a Q&A section here. If you look in the menu and you click on Q&A, you can ask questions during the session. Feel free to do that. I will have it open all the time. So often it has to focus on his presentation and answering questions, of course, but I'm going to ask him at any time you think you would like to ask him something. Saurav will be more than willing to share his experience. Please feel free to do so. And we will also try to make sure that every question will be answered. So coming back to today's topic, and we're going to record the session. That's just a short note here as well. It will be available tomorrow on the YouTube channel. I'm going to make it available tomorrow, so you can even replay it if you like. Saurav, why is that subject for you so interesting?
So while I was starting out in data science, I remember there were like three main fields, the supervised learning, unsupervised, and the reinforcement learning. And out of all the three, I always used to find reinforcement learning the most fascinating, because that's what I think is the closest to human learning, which is you learn via examples, you learn via performing a certain set of actions in your environment and getting feedback from whether it is good or not. If you look at a child who, let's say, touches something really hot, that's an action, and the reward the child gets is probably a burn on his hand or her hand. And that is like a reward which is negative, and that motivates the child to not go and touch another hot surface in future. So I think like fundamentally, like with supervised and unsupervised learning, I would say they are more prevalent when it comes to like industry use. However, the one which actually from the beginning caught my interest was reinforcement learning, just because of the nature of learning via examples and interacting with an environment. And I think recently reinforcement learning, especially combined with deep learning, has seen a huge surge in terms of resources, applications, and yeah, and I personally find it really intriguing and the most interesting branch of data science for me personally.
Interesting. So will we see some code this evening, or is it just more abstract presentation?
No, there will be code, and I would try to run a live demonstration of how the code performs as well. And yeah, I'm not sure if the expectation is set for participants to actually have the laptops, but I think I can give you guys a walkthrough from the code, and then we can see a live demonstration of a self-learning system.
Awesome. So we can watch it on our notebooks at the same time?
Yes. So the link is in the presentation. What I'm going to do is also share a link for the code in the comment section here, so that people who are interested can follow along. It's in Python 3 environment.
Okay,
So
guys, get your Python 3 environment up, at least now, or set up a virtual environment.
and for those
Do you
who
have
want to,
Anaconda running on your system, or what do you use usually?
I've installed Python 3 on my local system. I just run it via
Directly.
terminal, just a Python script.
Mm-hmm. Oh, yeah, okay, cool. Yeah, okay, awesome. I think I'm quite curious to hear what you like to show us. Take the floor, please.
Sure. And before I actually get into the presentation, yeah, I hope that everyone is doing well and their families, and keeping everyone safe. It is particularly a tough time. So, and besides that, I think Stefan and the rest of the AI and Pi team, I'm really impressed by the efforts that you guys have been making in kind of democratizing the knowledge of AI and machine learning. And it's really an honor to be on this platform. So let's get started with this presentation on hands-on deep reinforcement learning. So thanks, Stefan, for the intro earlier. So just to rewind, hi everyone, my name is Saurav Kaushik. I'm a data scientist at Uber. I used to participate heavily, not as much as I would like these days, on this platform called Kaggler. And I'm among top 500 Kagglers. Besides that, I'm a contributor to CRAN and PyPy, which are the open source package repositories for R and Python respectively, two of the most used data science languages. So one of the other thing I do in my free time is give talks like these and share with the community all that I have learned. With that, the agenda for today is going to be the following. We are gonna get a surface level understanding of what reinforcement learning is, and then we are going to dive deeper into a particular branch of reinforcement learning called Q-learning. And then we're going to touch upon a really important concept within Q-learning called catastrophic forgetting and experience relay. And once all of that is done and we understand the basics of the theory, and we can actually code it, what we're going to do is to actually code it and see it live in action, and then we can save some time for the question and answers. But feel free to ask any questions if you might have, as Stefan pointed out during the presentation. So let's get going then. So for those who might not know what reinforcement learning is, it's a branch of machine learning in which you basically have two entities, an agent and an environment. And an agent's job is to learn how to behave in an environment by performing actions or by interacting with the environment. And what it gets in return, so as you can see, so the agent is going to perform actions in an environment, and what it gets as a feedback is primarily the reward and the state, which is a representation of the environment. So at every point in time, the agent, well, there are classes, I wouldn't generalize it, but in most cases, the environment is partially or fully observable to the agent. And agent's job is to perform actions in the environment. And based on the rewards or the feedback it gets and the new state that it receives, which is a representation of the environment again, its job is to further optimize the action so that the reward is maximized. So fundamentally, you can think of it as like interaction between two entities, an agent and an environment, and an agent's job is to find the optimal actions to take in an environment so that it can maximize the reward. And how you can think about reward is it's a positive or negative stimulus that the agent gets based on its action in the given environment, which is represented by a state. So in this particular example, you can consider the Mario game as an environment and Mario as an agent. And the state would be representation of the environment, like the pixel location of, let's say, all the obstacles present in the game, or all the coins present in the game would all be part of the state representation of the environment. And agent, which is the Mario, going forward or backward is an action that it is taking, or jumping is an action, for example, that it is taking, and it gets a corresponding reward, which might be getting killed, a negative reward, getting a coin, a positive reward, or it might be neutral, just for one step that it takes forward, it does not get killed or does not get any positive reward. So that's like the primary gist of the reinforcement learning realm, like how the problems are usually set up. And to further understand it concretely, let's kind of go towards a simpler example. I assume all of you are familiar with mazes and all these puzzles that a maze has. So you have the sort of bits or the negative sort of locations on the maze, and then you have the positive locations on the maze, and then there's a end goal that you have to reach. So let's formulate this problem. Let's say this is our agent at location 00, and it gets and it loses, so it can go to the left, right, up, or down whenever possible, and it loses 1 point whenever it takes a certain action. So that and why this is important is because we want the agent to reach to the end goal in the minimum number of steps. Therefore, we are penalizing the agent for every step that it takes. So one to the right, left, up, or down, each step has a -1 reward associated with it. And if the robot steps on the mine, which are these bombs that you can see here, the game ends, and the loss is 100, or we can say instead the reward is -100 in this case. And if the agent goes to this power, it gains a +1 point. And if the agent manages somehow to reach this end state or the end goal, it gets +100 points as a reward. And the value, the exact value of these rewards can vary. This is like purely experimental, but let's assume this to be the scenario. So what we need for our agent to make rational or an optimized decision in each state is a representation of the whole board, the whole maze. And we need to have some understanding of, given the particular state of the maze, which is, let's assume this one, with feasible actions of going to the right or going down, what are the corresponding long-term rewards associated or long-term value proposition of taking a right move versus taking a move which takes the agent down, right? And only if we had some function that would give us for each particular state, let's say this one that the agent is in right now, and the corresponding action, which would be either going to the right or going to the bottom, if only we would know a particular quality index or some value representing the long-term reward of taking that action, we could easily just take the one which maximizes the long-term value. And that's how fundamentally these problems could be solved. So you can think of like a quality representation of each state and action pair called Q values, which is so Q value, which is guided by a policy, say pi in this case, for a state ST and an action that is possible in that state, let's say AT, is equal to the expected discounted cumulative reward, given that you take the action AT in the state ST. So let's break it down. What all do we have in this equation? So, so T represents the current timestamp, and we have T plus 1, T plus 2, T plus 3 rewards. And reward is basically the feedback that you get from the environment. So the rewards would be what we discussed here. So stepping on this particular cell, for example, would mean a negative 100 reward. Stepping on this would be a plus 1 reward. Stepping on this would be a plus 100 reward. So the rewards on the next timestamp, one after that, and another one after that. But there's a there's a lambda here. What it does is you take the value of the immediate reward you would get in the absolute sense, but you discount the values of all the future rewards you would get exponentially. So the next one would be lambda cubed r T plus 4 and so on. So why is that important? Because as you go further along on the time dimension, the confidence of the reward that you would get constantly, the variability increases, and therefore the confidence that you have decreases, and therefore you want to have some sense of long-term rewards for decision making. However, you do not want reward at each timestamp that you would get to be equal. You want to optimize more for the nearer rewards, and you do want to optimize for the long-term rewards, but you want to discount them. Therefore, this term is called discounted cumulative reward, which you expect from the future. So this is like the fundamental equation which defines the Q value. And let's forget for the time being how we would come up with the Q value. But let's say if we had a Q value in this particular scenario, then it would be really easy. We can check the Q value, which takes care of the future rewards that we would be getting if we go down this path versus if we go down this path, and we can check the Q value for this state and the action of going right, and compare it with the Q value of this state with the action of going down. And whichever is higher, we would just take that action, either go right or go down. And we will, in the next state, if let's say if we decide to go down as a next step, then in time t plus 1, we can again look at the Q values of going to the right, going to the bottom, or going back up. And then we can again take the action which corresponds to the highest Q value. And hopefully, assuming that the Q values are a true representation of the quality measure of a particular state and action pair, we would be able to solve this maze in the most optimum way possible. So that's like the fundamental sort of concept behind Q learning. Now, you might think, how exactly are we going to come up with the Q values for all these state action pairs? So you can imagine something as simple as a table, right? So let's say these are all the cells in so these are all the 9 cells, let's say in a 3x3 maze. And these are all the, essentially, these are all the states. And then you can, these are all these states in which you can have the agent present in. And then these are all the actions that the agent can take: up, down, left, and right. And let's say you initialize the whole table by zeros. And then you play a few episodes, which is do a few iterations of the game. And then you observe with the random actions that the agent takes, what exactly is the reward, and you try to optimize for the Q value. And after, let's say, a few episodes, you would have certain Q values which are non-zero. So for example, in state 2, taking an action of going down is corresponds to a positive Q value. Therefore, the agent should do it whenever it is in state 2. However, going left also has the same associated Q value, and we can decide randomly. But after iterating on several examples, you would have this full table where where the agent could easily pretty much do a lookup, like in an Excel spreadsheet, for if, let's say, the agent is in state 3, for example, and have all the 4 possible actions, up, down, left, and right, which it can take. It is going to compare the Q values corresponding to each action, and the obvious sort of looking for the maximum, the action with the maximum Q value is going to be to go left, and the agent will go left, and will do a lookup again, and will do a lookup again. And this works really well for small environments, like a simple maze, because you have a finite number of states that you can have, which is a representation of where all an agent can be in a fixed environment. But it gets really tricky when the environments gets complex, because the possible number of states could be really like diverse and vast, and the solution might not be always as simple as just running a bunch of simulations and coming up with a Q table that the agent can always look up to come up with a perfect solution. At this point, I'm gonna take a pause, and Stefan, you can tell me if there are any questions right now, or you guys can ask any questions if you have so far. All right, I'll assume there is no signal noise, and it's 100% transmission of knowledge. Cool. So let's keep Stefan, you're muted, I think.
Yes, we have no questions at the moment. I will pass on the questions you have. Someone looks like it's beautifully explained.
Great. Cool. So let's keep moving on. Now, some of you might be thinking, so yeah, this is the representation of Q tables. You can just do a lookup in any state and see whether going left has the highest Q value associated with it, or the action of going up has the highest Q value, or right or down. And you can just take an action, and that would be an optimal solution. Now, as I said, this does not extrapolate to complex problems, because the number of states that you might have could be endless. And that flies really well with the next sort of section in the presentation, and to the question that some of you might be having. That is, how do you create these Q tables? So
I have one question. How do we define the reward? Nada is asking.
Sure. So let's in this slide, what we are doing is we are assigning rewards for the agent to be in each of these cells. So in this, to be in this cell would mean a reward of -100 because the game ends and we want to penalize the agent so that it learns to not go into a state which has a mine. Uh, this cell, for example, has a positive reward of +1. And the end state, of course, has the highest positive reward because that's the terminal condition where the game ends. And we have successfully won the game. So,
But the robot is not aware of the content of a cell, right?
sorry.
The robot is not aware of the content of a cell.
Yes, the robot, before taking action and entering a new cell, is not aware of the content of the next cell. But we can see it, and we can guide the robot to make a particular action in either of the 4 dimensions. So like, or rather up, down, left, or right. And sort of, I think the question might be on how exactly do we come up with these values of -100, +100, and +1. So what we do is we actually, like this is, I would say, experimental. And a certain reward scheme might work for really well for a particular problem and not for the other problems, but this is something which could be tweaked, and this is something which can actually help the algorithm converge faster or slower. However, like one general strategy always is to give positive reward for things that you do want the agent to do more often, and negative reward for the things that you want the agent to not do more often going forward. That's like a general strategy. The actual values could be experimental.
Walter is also asking if a robot moves randomly around in order to fill up a Q table. Is that correct?
Exactly. So going back to the slide, so you initialize a Q table, and then you choose an action which is mostly random. And what you're trying to do is basically explore all the search spaces possible and explore all the states possible. And it chooses an action randomly, performs that action, measures the reward that it gets, and update the Q table. And you just keep doing several iterations, and after that you would have a reliable, good Q table which you can hopefully always just look up and take an action based on whatever action corresponds to the highest Q value in that state.
I got an interesting question from Robert as well, especially for the flashlights here. If the lighting rods gave 2 points and the robot came up with a strategy of going in and out of a lighting square, would that be a strategy?
Sorry,
Yes.
can you repeat?
What if the lighting rods gave 2 points and the robot came up with a strategy of going in and out of a lighting square? So it's just moving out of a lighting square, going up again,
right.
up
Yeah,
again.
I think, yeah, that's an interesting sort of case where actually in a couple of iterations, I remember reading a few papers in which if you give, so there are a few things here. Let's go back. So this is like a really interesting question indeed. So we can play around and tweak these rewards. If let's say the lighting has, let's take it to the extreme case, has +100 reward, the same as the end state, right? The agent would have no motivation to actually go to the end state and win the game. It will try and keep going to these light cells and getting 100 points, which is equivalent of ending the game. And this has been observed to be a true phenomenon in several sort of games which use reinforcement learning, that if you do not do 2 things, then it actually just engages in the environment to maximize the reward, which could potentially be infinite. The first thing is there should be a penalty for each action it takes. So if you want the agent to solve the game in the minimum time possible, then you should be penalizing the agent for every step or every action that it takes in the environment. Therefore, it has a motivation to finish the game and win the game in the shortest time possible. And the second is the distribution of rewards should be such that in an ideal case, that the winning the game has the highest reward compared to other competing positive rewards of staying in the game and doing something like completing a mission, or in this example, stepping onto a light cell. So if it should be designed in, the reward system should be designed in a way that there is like motivation for the agent to actually successfully win the game. Otherwise, you would observe a very different behavior from the agent.
Daniel is asking if initial position of a robot is also randomized, so it's always a corner position, or is it a place somewhere in the square?
Absolutely. So that's a really good question, and that goes back to how fast do you want the algorithm to converge. If the starting position is always the same, then you can have an algorithm which converges really fast, because the variation in the states become more predictable and less. So there's like less variation in the states. But if the starting position is randomized itself, and you can go like further down this lane, that the position of the end goal and all the sort of bits and the positive rewards might be randomized as well, then you would have a lot of variation, which would require more iterations of the random action taking and iterating upon this learning process. It would require more of those iterations to for the agent to come up with a good policy that it can just follow.
And Patrick is asking if a Q function is so named because it gives the cumulative rewards.
Last time I checked, I think cumulative starts with a C, not a Q. But I'm not sure, but I think
sounds like a Q.
But I think Q is, please don't quote me on this, I'm not sure, but it is supposed to be a quality measure of taking a certain action in a certain state. Yep.
Thank you.
All right. So thanks for those set of questions. So let's see. So if we have created this Q table, then we can potentially solve all the problems. But some of you might be wondering that you were told that this is about deep reinforcement learning, and we are building like Excel-like tables in this talk. What are we doing? Are we off track? So this is indeed about deep reinforcement learning, and all of that was actually important to give you guys a sense of how the Q learning works fundamentally. And as I said, there will be environments which will be complex enough that you cannot have a finite states to represent the entirety of all the states possible. So all these states in an environment might not be finite. It might be really complex, and there might be infinite number of possible states where you cannot actually create a Q table, but you need some other estimator because you cannot just randomly take actions and learn all the possible Q values corresponding to each state and action pair, because there might be infinite combinations. And one of the best ways that I believe all of you must be aware of creating estimations would be to use deep learning. And that's where there's this fundamental sort of fit between deep learning and reinforcement learning, which comes together and is called deep reinforcement learning. And the equation you see on your left is what makes it all possible. So,
sorry to interrupt you again. So how would you distinguish between deep learning and deep reinforcement learning? What's the difference?
So deep learning is, so deep reinforcement learning is like a sub branch where you combine, so I think this would logically fall under the reinforcement learning tree. And just like Q tables is one of the ways that you can estimate the Q values for each state action pair. Deep learning is another tool that you can use. Potentially what you can also use is regression or decision trees, because the idea here is to estimate the actual Q value of something. And that's where deep learning kind of is a good plug to reinforcement learning. And it could have been decision tree reinforcement learning. It could have been linear regression or logistic regression reinforcement learning for that matter. But Yeah, so I think the fundamental difference is deep learning is a field in its own. However, deep reinforcement learning is specific to applying deep learning in reinforcement learning problems. So yeah, coming back to this equation that you see on your left here. So let's see. So you have so what you're trying to do is you're trying to learn the Q value corresponding to each state and action pair. And since you cannot iterate through all the possible state and action pairs because they might be infinite or too big to compute, what you're trying to do is trying to come up with an estimate for each state and action pair, and that will be your that will be represented by a Q value corresponding to that state and action pair. So what you're doing is you are coming up. So let's look at the right hand side. So you're starting with the so first of all, you randomly initialize, just like in any deep learning problem, you would randomly initialize all the state and action pairs Q value. So you'll have a random value, which is not at all a good policy to be used for taking actions in an environment. So you will start with that. And what you're going to do is have some sort of a learning rate, which is the alpha here. And you're going to take actions in each state based on whatever you know right now, which at the beginning would be a random, which will be a random sort of algorithm which spits out a random value for each state and action pair. So you're going to take the action, whatever action is suggested by the current model, which is totally random at this point, in a particular state, and you would observe the reward. And you would multiply the learning rate with this whole thing, which is reward plus the discount factor gamma into the maximum or the max of the Q dash, which is actually this might it might be better to take a step back because this might get complex otherwise. So fundamentally, let's assume you start with a randomly initialized deep learning model, right? And that governs what actions you take in each state. And you are in a particular state S, and the model suggests to take a particular action A. Now Q dash is, and you have a corresponding, Q value, which is, let's say, Q here. Now, after taking us action A in the state S here, you enter a new state S dash in which you might take another action Q dash, and you might have a you'll have a Q value Q dash in the next particular state for different actions. So what you're doing here is, and if you'll go back to this equation, then Q value is defined as the expected reward of the of taking as action A T in the state ST. And if you think about it, then R T plus 1, which is the immediate reward you're going to get, is something that you can figure out by taking a particular action. As soon as you take an action, which is, let's say here, as soon as you take an action, you immediately get a reward. And that is a true entity. So even though you are starting with a random initialization, you do have some true value, which is which represents whether that action was good or not. So you take R, which is a reward, the immediate reward for taking an action in A in state S, and then you add it with, and this is kind of like, we know it is random, but we are going to still use it because that's a best guess. So we are going to take the maximum. So you guys remember how Q value is like a cumulative representation of like all the future states and actions that you might take. So this hopes that from this point on that you would take a particular action, and then you would continue to take optimal action. So you don't need to worry about what the reward might be 10 actions down the line. You just care about a particular Q value, which is supposed to be a representation of all the future sort of branches that might open up in that particular subtree. So what you're saying is that similarly, I'm just going to rely on the Q value that I have, which is totally random, by the way, at the beginning of this equation. And I'm going to rely on it, and I'm going to take that and multiply it with a gamma, which is a discount factor, and then subtract the actual Q value. So what you're doing here is, so this would have been your Q value, the immediate reward plus the discounted rewards from the future Q values. And you're adding them up. And just to get the difference of the actual versus totally random, you're subtracting the random Q value, which you know right now, from this sum, and then multiplying it by a learning factor, which represents how strongly do you want to or by what factor do you want to update the algorithm, and then you're adding that to the random value that you have. So what you might have realized is this thing at the beginning of the algorithm is going to be random. Similarly, this thing is going to be random, basically from a random initialization. And similarly, this thing, which is same as the first term, is going to be random. And we are doing this. We're using this equation to come up with a new Q value, which will be slightly less than random. And the reason for that is the rewards are actually the true rewards that you get by taking action A in state S. So even though you start with a bunch of random values here, you're adding some sense of signal in this noise, and that makes up your new Q value. And iteratively doing this often enough is gonna help you estimate the actual Q values. Now, this was slightly tricky, so I expect there to be a few questions. Stefan, can you help me if there are any questions? You're muted, Stefan.
Asli, hi. I gave you the right to speak. You sent a question.
So I just wanted to know whether the maximum here on the states, following states, or the maximum is on following on a fixed states on the actions.
So maximum is for the state action pair, and maximum kind of represents the maximum expected future reward. So the action is not specific, but it represents that you're going to take the action which corresponds to the maximum Q value in the state S dash.
Okay, so all the possible states and all the possible action that
this is like
this from this point.
It's a pair.
From the pair. Okay.
Yeah, exactly. And think of it like delaying the problem. You're not solving the problem right now, but you're delaying it. That okay, in future I'm going to take the most optimum action. Yeah.
Okay, thank you.
Anna, I also gave you the right to speak. You had a question previously regarding the rewards and experimentally rewards. Would you like to speak up? Khan?
You can unmute yourself, Khan. I think you're muted right now.
Khan, yes. You just have to unmute. So we can hear you. I can repeat his question just because he posted it here in the Q&A section. He says, you mentioned that the rewards are defined experimentally. Can we say that reinforcement learning is somewhat supervised approach? If we take DeepMind's AlphaGo, do we have a Go player sit there and evaluate each move made by the model? Can reinforcement learning models be biased?
Yeah, certainly they can be biased, and as I said, how fast they converge and how well they perform is also dependent on how the rewards are defined. And therefore, it is an experimental thing because you can tweak the rewards a little bit and you can observe different, like difference in performance of the algorithm. Can it be treated as a supervised learning problem? They could be creating rewards. I think this is closer to like an optimization problem, which could potentially be solved using supervised learning. Like for previous set of problems, if you know what rewards work best, then for this new environment, let's say that you do not know how to assign rewards to, what could be the best way to assign rewards. So you can technically convert it into a supervised learning problem, but that would be on a meta level, which is defining the rewards.
Thank you. Robert, you also had a question?
Yeah, I just want to ask if the maxQ function takes into account all the possible actions in the next state.
So max Q dash is not different from the actual Q values, which is it takes all the, so this is the expected discounted cumulative reward. So you're I think the fundamental term is the cumulative reward. So this is assuming you take the best possible actions according to whatever policy you have going forward. You would accumulate several rewards, and then you would discount the reward based on where they come on the timeline, and then you would sum them all up, just like here. So that takes into account all the future expected discounted cumulative reward. So what this says is that once you land in state S dash, you would continue taking the optimal actions, and they would correspond to a particular value, max Q dash.
Robert, fine with your answer?
Yeah, I'm still a little bit confused about that.
So you're still confused, or I think you get your way through? Are you still confused?
What exactly is so confusing here, Robert?
Like, all right, so we have this function Q of S and A, right? The state and the action we're taking right now. So we took an action, and then max Q is the next, like S prime and A prime are the next action and states.
Right.
Right, but how do you know what's the next action you're gonna take? Like, you know the state because you made an action, but how do you know what's the next action?
Right. Awesome. So exactly. So I know the state, I don't know the next action I'm going to take, right? But let's stick with a maze example. In that, we'll have 4 possible actions that we can take in the next state, right?
Yeah.
So what max Q is saying is that I'm going to take the action which corresponds to the maximum Q value of all the 4 actions. So this is like arg max, if you think about it in Python terms.
So then the follow-up question is, what if the action you're taking is something continuous, like the force at which, I don't know, maybe the robot was throwing rocks or whatever, and it was a continuous action?
Yeah, it could be a continuous action which will just explode your sort of Q table, if you think about it that way. And this will have like infinite possible actions if it is a continuous scale. Therefore, it's like useful to break it down into discrete intervals. So yeah, I don't have I don't have anything else but to tell you that if it's a continuous action space, which means like there could be infinite number of actions you can take, then it'll be really hard to learn. And therefore, way around will be to actually break it down to discrete action space.
Oh, okay, thank you.
Reinhard, you had a question regarding the Q values.
Mm-hmm. Yeah. So am I right in the assumption that basically you are still using your Q table and you are essentially fine-tuning the Q values based on the maximum reward and kind of like propagating it back to all the other fields until it kind of stabilizes? But I don't see a neural net anywhere here.
Okay, yeah. So I think, yeah, that's a fair question. So let me call it out again. So we have moved away from the Q table starting from this slide. So what you're doing is you have a neural network in which what goes in is your state, a representation of your state and actions. And what comes out is let me rephrase. So what goes in is a representation of the state, which could be an array representation. And what comes out is the Q value regarding all the possible actions. So think of it like if the state is represented by a 10, like an array of size 10, then you have a 10 starting 10 nodes in the first layer, and the last layer has 4 nodes in which each corresponds to the 4 actions that you can take. And what it spits out is the Q value corresponding to each action. So the neural net, like think about a neural net in that sense.
Isn't it more like a neural net with just one layer where basically the input is the output, it's the Q value, and you're just fine-tuning one layer?
No, so for this example, let's say the states are represented by an array of size 10, as I said, right? So you have the first layer, which is of how many nodes there would be 10, right? One for each cell in the array. And then you can have several layers. And then the last layer would be equal to the number of possible actions you can take, in this case 4. So you would have 4 nodes corresponding to each action, and the value in each of those nodes would ideally be the Q value corresponding to that particular action. So you have so I just defined what the first layer will be and what the last layer in the neural net will be, and then you can have like several layers in the middle.
I worked previously on similar reinforcement problems but so the concept was to have a neural net where it was basically the current state is the input and the action is the output, and and the Q there would be no Q values. The Q values is the neural net figures out the Q values, but it's not kind of a Q values table as we saw it here.
Okay, I cannot comment on that, but what I can tell you is that I'm gonna like in a bit I'm going to share the code, and I can show you in the code in Python how exactly it is implemented. But the fundamental idea is once you know the Q value corresponding to each of those actions as the output of the neural net, then you can just do the argmax, and you can just figure out which action corresponds to the highest Q value, which is pretty much consistent with how we have been thinking about the whole problem.
Yeah, maybe for this problem, it's most efficient to do it.
Yeah, I mean, totally. Like
maybe to make
this concept
for this one.
Yeah, this concept could easily be molded. I mean, we can easily just do an argmax on the last layer and just spit out the action which corresponds to the highest Q value to make it exactly like what you mentioned.
Okay, last question from Deepak, and then I think we should let you go forward.
Saurav, I was wondering if there's a relationship between rate of learning and the quality of results that you get. So if I was to tweak the rate of learning, or maybe by extending the time to complete, do you get better quality of results?
Yeah, that's a really good question. So, and this is probably a really good opportunity to also emphasize on one thing that is like really important to call out. So if you look at this term, this is nothing but us breaking down the Q with S and A. So this is us breaking it down, because if you remember, QS is nothing but immediate reward plus a discounted sum of the future reward. So it would be RSA plus gamma R T plus 1 or R dash S dash A dash plus gamma square R double dash S double dash A double dash. So you can open it up. What you're doing is just opening it up by one, because you do know something which is like ground truth. And what you're doing is, this is the real, like slightly more real representation of the Q value, which you're and from that you're subtracting the random Q value that your model is aware of. So you're taking the difference essentially. So this is you can think of it like 90% noise, 10% ratio, and you're subtracting the value you had from 100% noise. And this is the difference basically. And you are using a learning rate here, and you are saying that, okay, I've learned that the actual Q value is slightly higher or lower, but I'm not gonna exactly update by the same amount in the original Q value. You might choose to do it, go ahead with a learning rate of 1, which is that if the Q value previously used to be 1, and the difference that I'm observing between the slightly more truer Q value versus the one which is pure noise is, let's say, 0.1, then I'm going to apply some learning rate on it, and I'm going to update my new Q value by adding the resulting total to the random one.
Okay.
And yes, indeed, varying it will change the time it requires and the quality of the performance as well.
Yeah. Okay. Thank you so
Thank you.
much. Yeah.
And from a logistical perspective, Stephen, how much more time do we have?
Continue, just go on.
Okay.
It's 7:30, so
Okay.
half an hour at least.
All right. Yeah, this should be good. So yeah, so in very simple terms, again, just to simplify it, you broke down the Q value here because you knew certain ground truth. This is something you still don't know, and you are just randomly filling in the values which you have from the initialization phase, and then you're subtracting the random Q value to come up with the difference, which is what you want to multiply by a learning rate, and then update to the original term, and that will now become your new Q value. And we are going to actually do it in the code as well, and hopefully that will make things more clear, if not already. One sort of important concept that I would like to sort of call out is called catastrophic forgetting, and the way around that is going to be experience relay. So what happens, just like a shortcoming that we need to overcome, which is, let's say this. So let's say this is what the algorithm is trying to learn. Like this is the state of the maze, right? Now, in most of the cases, we would have a random initialization of the maze as well for different examples. In this particular example, the agent is in this particular cell, and going to a right would mean a negative reward of 100. Minus 100 would be the reward, right? But let's say the next state that the next environment that the action that the agent comes in and comes up onto the same cell, but in the next, since we are now randomly initializing all the other elements on the maze as well, this might be the end state, right? And from the previous example, the agent would remember that, okay, in this particular cell, taking a right would mean a negative 100. However, since the maze has been shuffled and randomized, this time it is it actually is a plus 100 reward, but the agent will never take it because the immediate experience of the agent tells that taking a right would mean a minus 100. So that will mean the agent will not be able to learn anything properly if it is provided with an example and then counter example under the same circumstances. So taking a right, if it means a minus 100 in one example and in another example it means plus 100, then the agent would not be able to learn the true value of taking an action right in that particular cell. So, and that's like a really big problem, which we do not face in supervised learning because we use randomized batches. So even if there are examples of in supervised learning, let's say there's an example of, okay, these set of features gives you a 0 outcome, and very same set of features also give you a 1 outcome. Imagine like credit card fraud. Two people with exactly same feature set, one of them default and the other one do not default. And if there are several of these counterexamples, then it'll become really hard for the model to actually learn anything. And the way we get around this problem in supervised learning is by using random batches, and that's something which we are also going to do here. So rather than feeding the experience from each run of the game onto the model, what we're going to do is actually store them in a queue, and then do an experience relay, which is as it sounds, we're going to play it one at a time. We are just going to pick a random set of observations, and we are going to feed it into the model. So this is what we're going to do in like concrete terms. In the state S, we'll take an action A. We'll observe the new state st+1 and the corresponding reward rt+1. We'll store all of this as a tuple st+1 and rt+1 in a list, and we'll continue storing all these experiences up to a certain length. And once it is filled, let's say 40, for example, we would take a random subset, and we will have, out of that, we would come up with an X train and a Y train, and then we would feed them into for a batch of training into the deep learning model. So this is like an important concept that you would see in the code, which is what we use to get around this problem of catastrophic forgetting, in which the model might not end up learning anything. So with that, let's dive into a real problem. So what we're going to do is, I think some of you might be aware of the OpenAI chimps, which is an environment, an interactive environment for creating reinforcement learning agents. So the environment that we are going to actually focus on is the cardpole V1 environment. And here are like some of the specifications of the environment. So like fundamentally, it's the task is to balance a pole on a flat surface, and sort of the rules of the road are following. And I think this, so you can go to the GitHub page, which kind of gives you a nice description of all you can do. So the observations, which is kind of the state representation of the environment, are going to be this. So this is what you're going to get back from the environment. So I'll go back a few slides actually. This is actually the first one. So the environment is going to give you the state representation and a reward. And this is the state representation. So you're going to have 4 values. First one is going to be the card position on the screen. The second one is going to be the card velocity. And these are like the min and the max ranges. Then you will have the pole angle, and then you'll have the pole velocity at the tip of the pole, which can go from -infinity to +infinity. So these are all the, this is the array of size 4 that you would get, which is a representation of the environment. And you would get a corresponding reward, which is just +1 for each step until you actually reach a game terminating condition. And then going back to the slide, what you can do is take actions that influence the state and the reward, right? So the actions you can take are following. So 0 or 1, which 0 represents pushing the card to the left by 1 unit of force, and 1 represents pushing the card to the right by 1 unit of force, right? And I think here are a few comments about the episode or the game termination condition. So these are the termination condition. So the pole angle, let's see, if the pole angle is more than 12 degrees, the game would terminate. If the cart has moved 2.4 units to the left or to the right of the center, the game would terminate. Or more than 200 seconds have passed, the game would terminate. And sort of this is a good representation of what the environment is. And this is on their website here. They also show a random a random simulation. So this is a random agent which takes actions randomly, and you can see there's a starting position, and then the pole starts falling, and the random agent is trying to move the black part to try and balance the pole. And of course, since it's taking the actions randomly, it does not do very well. And what we're trying to do is to actually try and build an agent which actually is able to balance the pole for 200 or a higher number of frames. So with that, we can dive into the example. So initializing a few variables here. So the game name, which is which from the OpenAI is cart pole v1. Then you have the learning rate, and then you have the discount factor gamma. Epochs here is this is not total number of epochs. This is each individual epoch that you would be feeding in. The batch length is how many observations would each epoch train on. So you're seeing 10. And then we have this queue that we discussed that we'll keep storing all the values in. That's going to be of a really high value. Now, what we are also going to do is that so we'll start from a totally random initialization in the model. And as it actually starts going further, we would, okay, this is probably another topic that we will need to touch on. So there's exploration and there's exploitation. So each action that you take based on what the model suggests is called exploitation, because you have some knowledge of the environment and you are exploiting that knowledge and taking actions based on what the model suggests. But what you also need to do is exploration, especially early on, because you do not want the model to think of it like a tree. You do not want a model to get too focused to find the local minima and just keep taking the not explore the rest of the possibilities. And therefore you want especially early on, you want the model to actually have a high exploration in which it just takes actions randomly and observe what happens. But eventually you do want the model to also get to a state where it is taking actions mostly based on what it thinks is right. So this is all these three values represents how we are going to handle the exploration aspect. So the exploration max is going to be 1, and which is 100% of the times, and the min is going to be 10% of the times. And then we're going to put in a decay function which decays by 5% each time and just keeps 95% of the original value. So and to sort of summarize, we are going to start with 100% of the actions being random that the model take, and then we are going to keep going down, and the lowest would be where we take just 10% of the actions randomly, and everything else is governed by the model. And this kind of represents some top bounds for how many episodes we are going to have. We're going to play how much maximum reward, after which we'll stop the simulation, and how much reward as you see, which is the winning condition. The solve reward is if you reach 195 frames or 195 in the reward, you have effectively solved the game. So we do a bunch of steps here in initialization, and then what we are doing here is defining a deep learning model, which is following. So the first layer has the input shape, which is same as the observation space. And if you'll go back here, and I'll go back to the source. So this is the observation state. So you have a column, rather, you can think of it like an array of length 4, which has all these 4 properties regarding the environment. So think of it like a representation of the environment. So you have that. So you have the first layer has 4 nodes, and then you're adding more layers. So from right here we go to like 40 nodes in the second layer, and then we keep it the same. It's like fully connected. Another 40 layer, and then we are putting it all back and making the size same as the action space. If you recall, how many actions can we take? 0. So like there are 2 actions. We can push it to the left by 1 unit or push it to the right by 1 unit. And these are like discrete, non-continuous actions. So then the last layer is 2 nodes, each of which represents, and the value on each of the node would mean the Q value, which would corresponding to each of those actions, which is 0 or 1. And yeah, so we initialize this model, and it would look like the 4 nodes. The first one has the 4 layers. The first one has 4 nodes. The second one has 40 layers. The third one has 40 layers, and then the fourth layer has the fourth layer has the fourth layer has 2 nodes in it, which corresponds to the 2 actions that we can take. And this is simply just defining how you're going to take actions. So this looks at the exploration rate, which we have touched upon earlier. So like this is going to keep decaying, but it'll start at 100%. So 100% of the times it'll be taking a random action. As it'll start decaying, and let's say it gets to 50%, then 50% of the times will be falling back to this else statement, which will take in which we'll take an action based on what the model suggests. This is just a simple step where we remember, or in other words, where we append in our memory this particular list that we discussed. So a state, action, reward, and the next state, and a flag called done, which is whether it's game terminating or not. And this is the experience relay part, where what we're doing is, so unless the memory is, unless we have the required length, which is the batch length. So if you look here, batch length of 10, unless we have like 10 observations, we are gonna keep filling in the memory. And as soon as we have 10 and as soon as we the memory, let's see. So this is if the memory. This is if we have more than 10 observations in the memory, then what we're going to do is take out a batch, a randomly sampled batch. And so for the first time, when we have 10 observations, it'll take out all 10. Of course, it won't be sampling because we are taking a sample of size 10. But let's say in the next iteration, it has 15 observations, then it'll take 10 randomly from that group. And as the memory keeps growing, we'll always be randomly selecting 10 observations. So we'll take out a batch, and then we'll start with a for loop for each of these state, action, reward, and next state combination in the batch. What we're going to do is we are going to calculate the Q value first of all, and this I'll put this on screen. So it is nothing but what we discussed right here. So we have the QS here, which we take out right now. So this is the Q value as the model suggests, which in the beginning will be totally random. And this handles the game termination condition. So if the game is terminated, then just update the reward completely. But if the game is still going on, then what you do is the update term, which is in this equation, this is the update term, everything inside the bracket, which later on is multiplied by the learning rate. This is the update term that we spoke about. So you're calculating the update term, which is the reward, which you see here, the reward in taking the action A in state S, plus the discount factor, the gamma, and into argmax, which is which is from the model for the next state. If we do a prediction, we are going to take the Q value, which corresponds to the action that that maximizes the Q value itself. So this is the Q update term. And what you do next is that for that particular action, you put in this Q update term, and then based on this new Q value that we have learned here, the new Q value, we are fitting in the model again. And this is the experience relay part, which we call in like in this a while loop several times. And this, so this is probably the most complex function in this whole code. And then we have a simple update exploration rate where we pretty much follow an exploration decay to keep lowering the exploration rate as we move through our simulation. So fundamentally, so this is like the main while loop, in which let's see. So we are going to render the environment when we play, so that we can see in real time how the model is performing in terms of managing the card pool. And let's see. So now we are just going to call a bunch of. So let's go from the beginning. Let's say. So we start with episode the initialization of the episode variable to be 0, and then we define a bunch of like thresholds, or rather the upper bound. So the solved score to win the game is 195, and the best score is 500, after which we are going to stop training. And we're going to have a flag which is, has the model reached the best score yet? And if not, we'll keep training. But as soon as we are able to reach the best score of 500 here, we'll just stop training. And then we initialize a bunch of lists that we'll be using later on. And we load the game environment, and then we infer the action space and the observation space from the environment that we'll be using as variables. And then we just create a instance of the class DQ and solver that we have defined here. And in this loop, what we are doing is the game is being played basically, and there are a couple of conditions like this one. Let's say episode less than equal to DQ and solver dot total episode. So and if you remember, we initialize the total episode to be 200. So it'll play up to 200 episodes, and for until the 200th episode is played, it'll the loop will continue going on. And and there's just one break condition, and then the second while loop is this, in which this so this one handles a game, and this while loop handles each frame or each step in the game. And what we're doing is, for we basically just run a simulation. So we take the action, we perform the action in the environment and get the corresponding observation, reward, like whether the game is over or not, a flag which is done, and some info from which we can actually infer the next state. And then we throw it into the memory queue we have by calling the remember function from the DQ and solver. And the order is as following. So we throw in the state first, which is the current state, and then the action we took in that state, the reward we got, and the next state we got. And let's see, and then we put the next state, which is called observation here, as the current state. And then we just check if the game is over or not. And if it is over, then we call out what the reward or the score in that particular game was. And if not, then we'll just pretty much continue doing experience relay. And after each step, we are updating the exploration trait. So this is like a quick walkthrough due to the time constraint. You have the code linked in the presentation that I hope Stefan is going to be sharing towards the end, and you can look at the whole code and understand it better and possibly reach out to me if you have any more concerns. But this kind of is like, as we discussed in this particular equation. So we are going to start with a random, so right here, if you see this machine learning model, then we are starting with a random initialization. This is how the model is defined, and we are starting with a random initialization. And then this is the only true value that we are adding. This is the only true signal, if you think of it that way, and rest everything else is noise. And our hope is that eventually doing this often enough, doing enough simulations, the model will be able to actually learn the true Q value representations for each state and action pair, and we can see whether it has done that successfully or not, as we will be observing the rewards we get from the environment, and that will be a continuous real-time feedback. Before we run this on this code, are there any questions? We can take them.
Yeah, thanks for sharing all that information. So basically the links, as you mentioned, so the link you posted already to GitHub and the link you sent me to the presentation will be included in the uploaded video tomorrow.
Awesome. Yeah.
So do we have any questions left? I can't see questions at the moment.
Come on,
So,
guys, this is complex, please.
yes,
I
I think
there must be a
everybody
few
is just
questions.
curious to try it out now.
Yeah, I do understand everyone to see the grand finale. Okay, well, in that case, we'll just, okay, I think there might be one question.
A few more words about the fit from GM.
About the model.fit. Yeah, so we have, so again, fundamental things about the model, which is defined, which is kind of initialized in the highlighted lines here. So it takes in, so this is the input shape, the shape of the input vector. So this takes in the observation space, as we were discussing earlier. And what it gives you is the Q values regarding all the actions that you could take in that particular observation space, right? And then all you need to do is, based on the Q values for the action spaces, you're just required to identify the maximum Q value and take the action which corresponds to the maximum Q value as the model has have spit it out. And what you do in model.fit here is so if you note here, what we have done is, so this is the garbage Q value we have. And then we are calculating an update to that garbage Q value, right? And we are calculating update as the absolute reward if the game has ended. But if the game has not ended, then the update would be reward plus the garbage value as predicted by the model for the next state again, right? And this update is what we are applying now. Like, this is sort of a key thing. We are not applying the update to all the Q values. We are applying the update to only the Q value corresponding to the action that we took, right? Because we only have the Q value corresponding to that particular action which we took. So think of it like this. You have a real-time environment which is being simulated, and you have a continuous set of a stream of rewards that you're getting back from it. And then you have a machine learning model which tries to predict the Q value corresponding to each state and action pair. Now, what you're doing is that you're using the model to get the Q values based on which, or randomly, you're taking actions, and then you're observing the reward that you're getting back from the environment. And what you're doing is you're taking the reward and you're updating the outcome in your model, as if you're telling the model that you predicted a certain value, but I'm going to update the actual environment, the actual output. And can you try and learn this updated output in the next batch? And that's what this model.fit does here, which is giving the state. So for this state, I know that you have, for this state, I know that you have already predicted this Q value, but now I've updated the Q value for one particular action that we took with this Q update, and I'm giving you the new Q value. So can you try and fit to this new Q value? So that's what's happening in this particular line.
Mayank is asking, Mayank, I just give you the right to talk. Why did you use the MSE loss here? Does using the MSA categorical cross entropy or any other loss affect the process?
Yeah, I think you could use different loss functions. I think in this case, since the Q value could, because it's not really classification, so entropy loss and all. So even though like in the end you have two nodes, but what you're really predicting is the Q value. So it's not really a classification problem, and therefore using mean squared error, root mean squared error might be slightly more appropriate than using cross entropy.
Thanks again. So no more questions. Guys, I did the following. I posted the link to Saurav's LinkedIn profile in the chat as well. So if you have further questions, would like to connect, go ahead. So
I think what everyone might also be interested. I think we can also just run this and see whether it works or not.
Yes, sure.
All right. So here it goes. So yeah, this is the whole file, and here's the we're just calling this game function, which has everything. All the parameters are initialized, and now is the time for the big test on whether it works or not. And so I'm gonna start running it, and we can observe. So this is the environment, and you can see like it starts, and it just immediately, since it's mostly taking actions randomly, it immediately falls off, and the new game is started. And you can observe the score here, and they're like low two-digit scores to begin with, but soon the model actually starts picking up signals, and it's not all noise, and that's when it like starts going closer towards, let's say, 100, as we can see. And it's and as you can also like see in the window here, it is able to balance it for longer and longer frames, and the score is kind of increasing here. So because it has learned from all the random like exploration that it did earlier. And yeah, so it is able to like balance it for much longer. So the last one was 313 frames. This one was just 114. So this will vary a lot because it might learn one thing. So right now it is struggling to avoid going to the left extreme. And I think it'll require a couple of examples to actually understand how to not go to the left extreme. And remember, since we are randomly just taking 10 observations, it might not immediately learn from its previous mistakes, but eventually it'll learn. So now you can see like we started somewhere here with like scores of 10, 15 in the beginning. And now we are now it is able to balance it for like almost like 300 frames in the previous example. And I've capped it at
Cool.
like 200 episodes, but I think based on what I've observed with this particular set of parameters, somewhere around like between 100 and 150th episode, it actually starts getting stable enough to score the maximum of 500 points. So this one is, so this is a good illustration of it trying to stabilize. The last one was 500 frames, and that's when it stopped. And now it has started making a mistake again, which it will probably, after several episodes, it will be able to stop doing again. But yeah, so that was like a representation of how it can actually, in a real-time environment, you can see the progress it makes. Yeah, any other sort of questions towards the end?
Yes, Ricardo had another question.
Oh, okay.
Ricardo, you're now free to speak now.
Okay, yeah, the question is, if you use this in a virtual environment, okay, that's clear, you can learn. But now, if you want to make a jump to the real world, as in Uber, it would be the cars, then you can no longer try randomly, because if your robot drops down or so on the wrong position, it's damaged and so on. And then is the question how you overcome this, as a simulation is not the same like the reality. So that's what I wonder, right?
Yeah, that's a really good question. Like I cannot like speak particular to the Uber example, but in all the problem sets where you do not have the luxury of, you know, like it's not a game, for example, and you do not have essentially the luxury to simulate like millions of examples in real world. There's like a particular like branch of like robotics which just deals with creating environments where you can simulate a real world environment. So think of like what you can, an engine you can potentially use is like a car racing, right? Consider games like GTA 5 or a Need for Speed, right? Those could provide a good simulation for real world environments when you do not need to actually put a, you know, a randomly a random decision maker agent into a car and into a real world. But you can actually still use simulation. So there are ways around it where you can potentially use like, you know, these environments to come up with observations regarding the real world.
Thanks. Asli, you also had a question?
Yes, I just was wondering, I mean, because we do not know and we start with a kind of finite state and then just try and error, we learn where to go. I was just wondering how this compared to genetic algorithms, for example, like evolution algorithms. So, I mean, it's different, of course, implementation is different, but do you have an experience one works better than the other, kind of?
Yeah, that's a really interesting question. I haven't like personally tried out those approaches on these kind of problems, but this sounds like really interesting. Yeah, I probably would be interested in seeing the results. However, I haven't tried out and can't share any experience on that point.
Okay, because I know, for example, for one case that there are some genetic algorithms that try to write like this movement kind of someone walking straight and learning straight based on the genetic evolution models. And it's like this example that you just produced now is kind of very, very similar. So I was just wondering.
Yeah, there are genetic algorithms being used in for RL problems as well. So I think this is something you can find online. I personally haven't tried out one yet.
Okay, thank you.
Thanks, Asli, for asking the question.
No problem.
Someone else? Any more? Any further questions? Okay, guys. Thanks again. For all those who would like to save links in the chat, click on the three dots in the chat box. You can save all links as well. Anyway, it will be posted tomorrow as promised. I would like to say thank you again to Saurav for just taking the time and being so patient with our questions.
No issues, Stefan. It's a pleasure to be here. And yeah, I'm really impressed by all the work that you and your team are doing to spread knowledge about machine learning and data science. And yeah, it's an interesting time, and hopefully people have more time to devote to their personal learning if they're interested in data science. And I'm happy. It's a pleasure to present to this audience.
Nice to hear that. I think it was a pleasure that you also presented code, and that we have now the possibility to train a little bit, test ourselves, and look at the code in more depth. Like it.
Yep.
Pretty much. Thank you very much again. And I keep you posted when it's up, and it's up on YouTube.
Awesome. Bye, everyone. Stay home, stay safe.